A bullet is fired straight at a can hanging from the ceiling, as shown in the figure below. At the same instant the bullet is fired, the string breaks and the can starts freefall. The bullet's initial velocity is v initial, and at an angle theta to the horizontal. The can's initial height is h, and at a horizontal distance r from the bullet. Can the bullet hit the can? So let's start by finding out the time it takes for the bullet to cross this distance r. So there's this kinematic equation that says that the displacement is equal to the initial velocity times the time interval plus 1/2 a/t squared, where a is the acceleration and t is the time interval. So let's start by breaking the bullet's initial velocity down. So if this arrow represents the initial velocity, we can break it down. We can break it down into its horizontal and vertical components. And if this is the launch angle theta, then this is the initial velocity times the sine of theta. That is the vertical component. And the horizontal component is the initial velocity times the cosine of theta. And you can use some trigonometry by saying like the cosine is equal to adjacent over hypotenuse and then manipulating that equation. And then you can find these. So in the case of the change in x, or the displacement in the horizontal x direction, the horizontal displacement is simply r, the horizontal distance r. That is equal to the initial velocity in the x direction, which is the initial velocity times the cosine of theta, and plus 1/2 a/t squared, acceleration. But there is no acceleration in x direction, so this part can be omitted. So the range, oh, sorry, I forgot t, or time interval here. So r is equal to the initial velocity times the cosine of theta times the time interval. We can solve this for the time interval to get the time interval is equal to the range, or distance r, divided by the initial velocity times the cosine of theta. And that is the value for time. And that will come in handy later. So I'm going to write it down here. Time is equal to the range divided by the initial x velocity, which is the initial velocity times the cosine of theta. So now that we have that, we can use this equation again, but this time in the y direction. So in the y direction, it's, let's say the change in y of the bullet, so the y displacement of the bullet, you can say that is equal to the initial y velocity times the time interval minus 1/2 times the gravitational acceleration times the time interval squared. And this is negative because the gravity is pulling it down. And we can replace the acceleration with g, since the acceleration in the y direction is simply the negative of the gravitational constant, or gravitational acceleration. And we can replace the change in y of the bullet with the current position of the bullet, or final position, minus the initial position of the bullet. That is equal to the initial y velocity of the initial velocity times sine theta minus 1/2 gt squared. And the initial y position of the bullet is 0 meters, since the origin of this graph is at where the bullet launches. So when it first launches, it's at 0, 0. So 0 meters in the x direction and 0 meters in the y direction. So this whole part can be omitted. So get that the y position of the bullet is given by the initial velocity times the sine of theta. Sorry, there's supposed to be a t. I keep forgetting the time interval. Times the time interval minus 1/2 gt squared. That's the function for the y position of the bullet. I'm going to write it up here. Position of the bullet is equal to velocity times sine minus sine half a sorry, 1/2 g t squared. And now let's use this again and solve for the change in y of the can. So that is equal to the initial velocity. Now the initial velocity of the can is 0 meters per second, since the string breaks and the can starts free fall. So it's initially it's kind of just dropped when the string breaks. There's no initial velocity that is given to it in the y direction. So this whole part can be omitted from our calculation. And as for the acceleration, it's minus 1/2 gt squared, which is the acceleration due to gravity in the y direction. So again, we can say that the current position, y position of the can minus the initial y position of the can is equal to minus 1/2 gt squared. And the initial y position of the can is simply its height, since it starts at a height h above the ground. So this becomes, let's see, minus h is equal to negative 1/2 gt squared. So the position of the can at any given moment is the height minus 1/2 gt squared. So I'm going to rewrite that up here there. The y position of the can at any given moment is the height minus 1/2 gt squared. So now that we have that, we need to figure out the change in y, or the distance in y position between the two. So now think about it like this. If you fire the bullet, it's going to go on a parabolic trajectory, and the can will be falling as well. This change in y is simply the difference between their y positions. So it is basically their difference between the y positions of the two falling objects. So for this case, it doesn't really matter if you do the y of the can minus the y of the b, or sorry, y of the bullet. I'm just going to say that it's the y position of the bullet minus the y position of the can. But it doesn't matter much. You might get negative value though. And as you've seen before, that is equal to this stuff that we figured out earlier. So we can simply just plug that into the equations for the y position of the bullet and the y position of the can. So this becomes the initial velocity of the sine of theta times time interval minus 1/2 gt squared minus h minus 1/2 gt squared. Kind of ran out of room, but if you'll notice, there's if you distribute this negative, there's two negatives, so this becomes plus, and so these two cancel each other out. So we can ignore this whole t squared kind of stuff and avoid that whole mess. So this simply becomes the initial velocity times the sine theta times t minus h. That's the expression for the y difference of height between them. If you remember, we found out t to be the range divided by the initial velocity times the cosine of theta. So we can plug that in for t, cosine theta minus h. Now if you notice, the initial velocities cancel, so it doesn't matter what initial velocity it has as long as it makes it across the distance r before the can actually hits the ground. So there's that. And that, if you notice, sine theta, if you multiply these two together, you'll get sine theta divided by cosine theta, which is simply the tangent of theta minus h. So that is the difference in y between the two. So I'm going to rewrite it here. The difference in y between the bullet and the can is equal to the range times the tangent of theta tangent of theta minus the height. Now, if we look at this, we can say that the tangent of theta, which is the opposite over the adjacent, is equal to h, the height, over the range. So by moving this equation around, we get that the height is equal to the range times the tangent of theta. So plugging this back into the equation, we get that the y difference is actually simply h minus h, the height minus the height, which is equal to 0. Which means that at any given moment, the can and the bullet are at the exact same y position, since there is no difference between their y positions. So the bullet will always hit the can. So the bullet will be able to hit the can as long as it is able to cover a distance r before the can actually hits the ground. And that is how you would solve this problem here.